This is video 3 for the topic 9.2, 19.1, electrochemical cells. Now we're moving from voltaic cells to what's called electrolytic cells. This is the SL portion for this set of notes. What are electrolytic cells then? First, let's go back and recap. Voltaic cells. Voltaic cells take the energy of spontaneous redox reactions and they harness it to produce electric charge or electric voltage. So as we saw in the previous videos, with a voltaic cell, you have two half cells connected by an external wire in which the electrons can then move through, and it's always going to move in the spontaneous direction in order to produce that voltage. Versus your electrolytic cell. This uses an external source of voltage or electrical energy to run a non-spontaneous redox reaction. So essentially think of a voltaic cell as a battery, okay? And you use up the battery, so all the forward spontaneous reactions are complete. Now it's a rechargeable battery, so you put it into the charger. And that now makes it an electrolytic cell because the charger, which is usually connected to our electric circuit, right, through a plug, forces those reactions to go in the reverse process, the non-spontaneous process, restoring or going from equilibrium back to the spontaneous reactions that can occur. So that's kind of how you compare those two. In an electrolytic cell, okay, the electrolyte, and now remember an electrolyte is something that has the ability to conduct electricity. That is the reactant in the process of the electrolytic cell. So this could be either a molten ionic compound, so an ionic compound in its liquid state, which is very hard to achieve, or a solution of an ionic compound, so an aqueous solution where the ions have the ability in which to move. So how this works, and we're going to see a diagram on the next slide, but you have an electric current. Okay, that electric current moves through the electrolyte. That allows your ions to move towards their appropriate electrodes that then can go through redox reactions. So one electrode is going to be the anode, the other electrode is going to be the cathode, and having an exchange of electrons occur. At those electrodes, you're going to remove the charges from the ions in the electrolyte, creating neutral elements. So the purpose for the really important purpose, not just recharging batteries, even though that really has taken priority at this point, but the real purpose of an electrolytic cell is separating reactive metals like sodium and potassium from their ores. And this is, again, gold. All these metals that we find in rock and ore, we need to separate them out, and we can do that through the electrochemical process, which is pretty cool. So IB does not require you to be able to draw an electrolytic cell like you have to do with a voltaic cell, but you need to be able to interpret and understand what is occurring in an electrolytic cell. So here we have the basic setup, right? So in our one beaker, and that is the big difference between electrolytic and voltaic cells, is electrolytic cells can occur in one solution, whereas voltaic cells need two half cells with two different solutions. In this one solution, you have your electrolyte. Right, so those are going to be your ions. Let's just say it's like a sodium ion and a chlorine ion, right? And those are just floating around. Whether they're in an aqueous or molten state, doesn't matter. All right, then you have inert electrodes. This means that the electrodes are going to be submerged within the electrolyte. That way they have the ability in which to interact with the electrons that are moving, but are not going to take place in the redox reactions themselves. So they're going to be made of an on-reactive metal like platinum or graphite. And then those electrodes are connected to an external circuit. And how we know it's an external circuit is this break in the line. And so this tall and short line represents that external circuit. Like DC power, right? The long line is the positive, the short line is the negative. And so that tells you essentially where the electrons are coming from and towards. So the positive end of the battery source or electricity source is going to accept electrons, right? And the negative end is going to give off electrons. So what's going to happen here is we're going to turn on our battery or our electricity source, right? And so this is going to produce electricity being passed in our electrolyte. Well, what happens is, so these electrons from the negative end are being given off and they're being pushed towards the cathode. Okay, so they're being pushed towards the cathode. Those electrons are going to accumulate on the cathode. Well, that is going to attract our positive cations, right? So like our sodiums. So our sodium is going to come over and it's going to accept those electrons and to create a neutral sodium atom. So we're getting a buildup of neutral sodium atoms. So our sodium is being reduced at the cathode. All right, well, that electric current is moving through, right? And so the anode is pulling electrons away. And so that means that this anode is starting to become positive, right? So our anions are going to get attracted to this positive metal, and they're going to, like chlorine, right, is going to deposit their electrons onto that metal, that positive metal. And so that those electrons can move back up into the power supply. So because chlorine is donating its electrons, they are being oxidized, which means we are starting to create chlorine gas, pure chlorine gas. So now we can siphon off these two very reactive elements into their standard states, which is pretty cool. All being worked by that external circuit. Because sodium and chlorine prefer to be in their aqueous or their ion form, we have to force them back into their natural form. And that is what an electrolytic cell does and how the basic operation works. So just like in voltaic cells, the redox reactions do occur at the electrodes. The negative electrode, the cathode, is where your metal, your positive cation, is going to be accepting an electron from that electrode to create a neutral element. And because it accepted the electron, it is reduced, right? So it is negative. That electrode is negative because it's taking electrons from the external wire. And those electrons are now being made available to the positive cations in order to make them neutral. The positive electrode, your anode, all right? So that, because it's a positive electrode, it's taking electrons from that electrode back to the power source, right? So that metal is becoming positive, attracting your negative anions. So that negative anion is going to give up its electron, it's going to become oxidized, producing a neutral element and then providing the electrons back into the circuit. The nature, so what we need to keep in mind, the nature of the redox reaction defines the electrode, not the charge. Because in voltaic cells, the charge of the electrodes are opposite. But the process that occurs there is the same. So I have a table. Looking at your anode and your cathode, okay, voltaic cell versus your electrolytic cell. So the anode, if you notice, no matter the cell you're in, you have oxidation occurring at the anode. But the charge of the anode is going to be different, okay? So in the voltaic cell, oxidation is occurring at the anode, and it is negative because the electrons have to be donated first in order to pass through the external circuit for a spontaneous reaction to happen. In an electrolytic cell, the anode is positive because electrons are being pulled from the metal and they need to be replaced. And that is how you get a negative ion to be attracted to the anode. Another major difference is in the voltaic cell, you're typically made of the metal is the element in which we're running the reaction, whereas the electrode in the electrolytic cell is a non-reactive metal. So differences there. The cathode, as you can see, reduction occurs no matter the cathode, right? So cathode is reduction. In the voltaic cell, the cathode is positive. Okay, so those electrons are moving towards the positive cathode. That's where the attraction is occurring, right? So that the electrons can be attracted over there in order to reduce the ions in that half cell. In the electrolytic cell, the cathode is negative because electrons are being pushed onto that electrode, attracting the cations to it in order to have reduction occur. So how do we go through and predict the products in an electrolytic cell? There are two processes. There's for molten ionic salts, which is the SL portion. Then there's aqueous solutions, which is the HL portion. So first you want to identify all the ions in your electrolyte. And based off that, based if they're positive or negative, you want to determine their migration. For the second, this one, if there's more than one ion at each electrode, the only time you're going to interact with this is in HL for aqueous solutions. Okay? If it's a molten solution, we can ignore this one. So in a molten salt solution, there's only one ion at each electrode. If you're in an aqueous solution, you're going to have multiple ions at each electrode, and you're going to have to determine which one is going to get discharged, so oxidized or reduced, based off their E theta value in table 24. Then write your half reaction that is occurring at each electrodes. So remember, electrons are released at the anode because oxidation occurs at the anode, and electrons are taken up at the cathode because reduction occurs at the cathode. Then you want to balance the electrons lost or gained to write your net reaction. And then the last thing they're going to ask you is consider what changes, visual changes you can see in the solution that you know that it's working, that you're getting the products you're supposed to be receiving. So we are going to go through multiple examples of this, so do not be worried about that. So for the SL portion, looking at molten salts, okay? So that means if it's a molten salt, it's a salt in its liquid state. And so the only ions present is the compound itself. There's no solvent, so you don't have to worry about any other ionization occurring. So the example in which we're going to look at, so we're going to have molten lead bromide. And notice I used an L to show that it's in its liquid state. So in its liquid state, that means we have lead ions and bromine ions. Okay, so now you need to figure out who's going where. Well, we know oxidation occurs at the anode. Oxidation is losing electrons, so that means it's going to be attracting your anions. So your anions are going to go to the anode. Your cathode is where electrons are going to be given up or given off, and so it's going to attract your cation. And so our cation is going to go to the cathode. So now we need to write each half reaction. Okay, so what is going to happen? So a half reaction for lead, because it's going to the cathode to be reduced, it is accepting electrons. And it needs to accept 2 electrons because it has a 2 plus charge. And we are going to get solid lead. Lead is solid at its natural state. So it is being reduced at your cathode. Bromine, and remember there's 2 of them because we had Br2, so 2 bromines, is going to the anode to be oxidized to release its electrons. So that means we're going to get Br2, which is a liquid in its natural state, and it's going to release those 2 electrons back onto the circuit to go back to the cathode. So this is showing that bromine is being oxidized, and it's being oxidized at your anode. So we can write our net reaction. The electrons are already balanced for us, which is a nice thing. And so we can cross out our electrons and we can write our net reaction. So this is showing us that Pb2 plus 2 bromine ions is going to give us pure lead and pure bromine. So any observable changes, what would we be able to observe? Well, at the anode, okay, bromine is brown. So we're going to see a brown liquid with this bromine smell. Bromine has a distinct smell. At our cathode, lead is a dull gray metal. So you're going to start to see a gray metal precipitate at it's actually going to precipitate onto the electrode itself, and so that we can take the electrode out and scrape the lead metal off. Now the problem with the process, one of the major problems in molten salts is because salts have really high melting points, like really high, which means it's very expensive to run these. And there's also toxic byproducts that could potentially be made. Vaporization, especially like collecting chlorine gas, sometimes if it's an ore that we have melted, there could be other things that we're now isolating. So there's a lot of toxic byproducts. What do we do with the remaining electrolyte of that ore? And so there's ethical issues involved here. But what we can do is in our solution, okay, to try to make it cheaper, we can mix two molten salts together, lowering the melting point of the higher salt, which is pretty cool. Then we make sure you choose a salt that has a lower E theta value on the reactivity series so that it does not get reduced. So what does this look like? All right. So we want to isolate sodium from chlorine. The problem is to melt sodium chloride, it has to be melted at 801 degrees Celsius. That is insanely high. What they have found is by mixing sodium chloride and calcium chloride, it will lower the melting temperature down to 580 degrees Celsius. That's doable. The reason why we can use calcium chloride is if you look at calcium's E theta value for its reduction reaction, it's negative 2.87 volts versus sodium, which E theta value is negative 2.71 volts. So because calcium has a lower negative value, it prefers to stay in solution more than sodium, forcing sodium to be reduced. So that is a valid salt in which we can use to isolate sodium. And the fact that both have chlorine, that just gives us more chlorine in which we could be making also. All right, so going back through the same process as before, what are we doing? So we have sodium chloride and we want to make it into a liquid, which means we have a sodium ion and a chlorine ion. Where are each going to go? Well, our positive ion, our cation, goes to the cathode. Our negative ion, which also is known as an anion, is going to the anode. You kind of notice anion, cation, cat. Might help you remember. So what's going to happen at each of these sites? So sodium is going to go to your cathode. The cathode is where reduction occurs because it's a cation, so it's going to accept electrons from the cathode, and it's going to create solid sodium. So it is being reduced. Chlorine is going to go to the anode, and it's going to accept, or it's going to donate its electrons, right? Because it's going to be oxidized into Cl2, releasing 2 electrons. So we need to make sure this one's balanced, right? And so it is being oxidized. So because chlorine's a Brinkelhoff and its natural state is Cl2, it has to donate 2 electrons in order to create Cl2. So for this one, to write our net reaction, we have to make sure our electrons match. So that means we need to balance our sodium half reaction so that we have 2 electrons that we can then cross out. Right, then we write our net reaction. So we have 2 Na plus 2 Cl minuses in their liquid state. And we are going to get 2 sodiums, and we're going to get chlorine gas being released. So what observations would we see occurring? Well, because chlorine's a gas, we're going to see bubbling, right? And it's going to have a chlorine smell too, because chlorine has a smell. For our sodium, again, it's a silver metal, so we're going to see a silver metal be precipitated at the cathode. And so that is how you go through and you work with the molten salts. And that's it for the SL portion of electrolytic cells.